So subsection 2, establishing the third. So as you have seen, the third law of Kepler is this: t squared over a cubed is equal to some constant k. So we are going to establish this equation. So projecting the equation 1, okay, onto the Tn axis gives, so actually, okay, we have already established this. So simplifying with mt and with r gives g times ms over r, which is equal to v squared. So we are going to name this equation 2. And from the other hand, from the other side, knowing that omega, the angular velocity, is equal to 2 pi over t. Okay, the angular velocity is equal to 2 pi over the orbital period, and the linear velocity is equal to r, the radius of the orbital, or the orbital, times omega, which is the angular velocity. So this has been seen last year. So this gives us that v. So if we replace omega by its expression, it gives us 2 pi r over t, which means that if we raise this equation to the square, v square will be equal to 2 pi square r square over t square. And we are going to name this equation 3. So we notice here that we have also another equation with v square. So equation 2 is equal to equation 3. This leads to the following equation: g ms over r will be equal to 2 pi square r square over t square. This gives, so rearranging this equation, t square over r cubed will be equal to 4 pi square over g ms, which is equal to a constant. Okay, so we found out that t square over r3 is indeed equal to a constant. So 4 pi is a constant, g is a constant, and ms is a constant. So we can calculate this constant. Okay, so we know that the gravitational constant is 6.67 times 10 to the power minus 11. It's a Système International. ms, the mass of this sun, is 198 times 10 to the power 30 kilograms. So calculating this constant gives 2.98 times 10 to the power minus 19 second square meter to the power minus 3, which is very close to the value found in the literature, which is this one. Okay, this value is more precise. Now let's move to the fourth section, section 4, motion of satellites around the Earth. So now we are going to focus on satellites around the Earth. So the same physics, the same study seen here, okay, applies in the case of the study of satellites around the Earth. We just replaced the sun with the Earth, and here the object with the satellite. Okay, so the same study, the same force, gravitational force, the same study, applying Newton's second law, projection of the equation onto the Freinet axis, the same study. So the same study in section 3, section 3.1, applies here. The only difference is the following. We only replace R with RT plus H, with RT being the radius of the Earth. So RT is around 6,400 kilometers. So this is RT, and H is this distance between the satellite and the surface of the Earth. As it can be seen in this picture, so R in the previous study is to be replaced with RT plus H, RT being the radius of the Earth and H being the elevation, or the distance between the satellite and the surface of the Earth, H. Now with section 1, subsection 1, putting satellites into orbits. So putting satellites into orbits enables it to have a uniform circular motion around the Earth under the gravitational force only. So to do that, it requires two steps. The first step is to reach a high altitude, okay, to escape from the atmosphere. So the atmosphere is the layer of air around the Earth. It creates friction, okay? So we don't want to get friction and to lose power, okay, in doing so. So we try to reach high altitude where the air is thin and minimize the frictional forces. So reach high altitude, escaping from the atmosphere. So minimize frictional forces due to air. And two, we need to release the satellite with enough velocity, V0, that should be, so this is V0 should be perpendicular to the trajectory, to the circular trajectory, and with value V0 should be equals to G times mt, the mass of the Earth, over R, RT, the radius of the Earth, plus H. All that under the square root. So this equation comes from the previous study. So we have seen here that V square is equal to GMS over R. This is the case of the Earth and the Sun. For our case, R should be replaced with RT plus H, and the mass of the Sun should be replaced with the mass of the Earth. So V0 is equal to this. So this is very important requirement to put a satellite into orbit. So we get high enough, at an altitude high enough to escape from the atmosphere, and we give it a velocity which should be equal to this amount, this precise amount. This way the satellite will have a circular trajectory around the Earth. For example, this way. Okay, so the last part of this course is subsection 3, geostationary satellites. So what is geostationary satellites? So it's an Earth orbiting satellite that appears stationary to the Earth, which means that from the standpoint of the Earth, the satellite appears non-moving, meaning that the satellite should be orbiting with the Earth at the same rate, okay? So it must be placed at an altitude of approximately 35,600 kilometers in the equator's plane with uniform circular motion. So the satellite should be placed in the equator plane, okay? The plane that cuts the Earth in halves at the equator, okay? So the satellite should be contained in this plane. So this is actually the plane, and should have uniform circular motion and should rotate in the same direction as that of the Earth, obviously, okay? So it must be going in the same direction as that of the Earth, which means from west to east. And at this altitude, one orbit takes 24 hours. So if the satellite is to be facing the Earth and appears on the Earth to be stationary, one orbit, which means the orbital period of the satellites, should be equal to 24 hours, which is the orbital or which is the time taken by the Earth to revolve around itself once. Okay. So these are the requirements for a satellite to be geostationary. So first, it should be at this altitude and should be in the equator's plane and with uniform circular motion, okay? And it should be going in the same direction as that of the Earth, from west to east.